Today, I'm pleased to introduce Dr. Halil Sezen, Professor of Civil Environmental and Geodetic Engineering. He brings expertise in structural engineering to the design, modeling, and analysis of structures and their components. Over his career, he has examined building collapse processes, rehabilitation strategies for concrete bridges and structures, and strategies to enhance sustainability characteristics of structures. Today, he will share perspectives about the performance of structures under extreme loads. I request that you please drop questions in the chat function at any time during the presentation. I will moderate those in the question and answer session that will follow the end of Dr. Sezen's presentation. So let us now welcome Dr. Sezen.
Thank you, Alison, for the nice introduction. And let me start sharing my slides. Kevin, just to make sure it's showing up fine, right? Okay, good. So, well, who am I? Although our department chair gave a nice presentation, I wanted to give my personal background a little bit. I started working at OSU in the Department of Civil and Environmental and Geodetic Engineering in 2002. And I worked and graduated, I don't know, 50 plus students, graduate students by now. And I also found out last night that I worked with 13 undergraduate honor students that they did research. So on the research side, those are the students that I worked with. And also over the years, I taught structural analysis courses, but I have been mainly teaching reinforced concrete. I love reinforced concrete. So in the middle, you see that 4350, 5350, 7350, those are my babies and reinforced concrete classes. I recognize some names. Probably you have taken that class if you graduated from OSU. I used to teach press-stress concrete, not anymore, but I also ended up loving bridge engineering that I have been teaching over the last several years. I have been participating and active in professional organizations, including ASCE, American Concrete Institute, Precast Concrete Institute, and Structural Engineers Association of Ohio. There are a few more, but these are the main ones that I actively participate. And I also saw that Kevin put my picture on my website. Thank you, from 2008. And now we can see that I have gray or white beard compared to how I looked like 16 years ago. So also it was a little bit difficult for me to reduce the focus of my research over the years, although I have been looking at performance of construction materials and structures. It looks like I looked at many different things, mainly buildings, and my background was reinforced concrete and seismic loads, but in Ohio, over the years, I looked into many different materials and structures, including bridges and culverts that I never thought I will be doing research in culverts, and I did, and focused on culverts for many years. And then under extreme loads, especially after earthquakes, I ended up investigating the behavior of industrial facilities, historical structures. More recently, actually, we had a couple projects on nuclear structures. So that was also interesting over the years. Today, I will also show you a few interesting research items or projects, I should say. We will talk about some rebar, concrete materials, things like that. So I just selected a few as an example. This is one current project that I want to make sure I put out at the very beginning. I'm very excited, and I have been spending a lot of time on this idea at this point. So the idea is everybody is aware of the standard solid steel bars right near the bottom of the slide. So the idea is, can we use the same area of the steel in our concrete structures, and then use the hollow bars that you see on this slide. The idea is, can we circulate some kind of heat through that rebar hollow bar? So in other words, if we can provide some kind of heat source inside the bar, we may be able to heat the heat the slab or pavement or whatever concrete member we have. So we are at the idea stage right now, but I have a student working on all the theoretical and other aspects of it. So the idea is to have two functions at the same time. These hollow bars are going to act exactly like the reinforcing steel in concrete structures and carry the tensile forces under bending. So we are not changing anything. As long as we provide the same strength and tensile capacity, it will do exactly the same thing. We talked to the manufacturers of those hollow bars. Apparently, they are commonly used at this point for drilling purposes or anchorage purposes in construction quite a bit, though they are available, but no one uses them for concrete structures. So if you look at the bottom drawing with those blue lines are representing our standard flexural or longitudinal bars. Our idea is to either circulate hot water or vapor that may be a little bit messy, but we found out that there are some heating cables or coils. If you think about your space heater, for example, in simplest form. And the idea is we can connect that cable to a power source, just switch the power during cold cold weather and just heat your slab. That's the idea. So then we started thinking about potential applications. I think the easier ones or the most critical ones are to melt the ice or snow on, let's say, roof of the parking garages in winter, or bridge decks. That's a major problem for us with black ice and all those things. And airport tarmacs, they spend a lot of money on that one. And if the idea works at those critical levels, then it can be also used in standard office buildings, commercial buildings, as long as they are reinforced concrete. So we are at the stage that I'm working with the office at OSU. This is an intensive thing that I learned quite a bit about business. So we have been talking to a lot of companies in different segments and learning about the whether this idea will work or not. And we learned a lot actually during that process, corrosion and durability and heat source and things like that. And OSU is helping me a lot. And I learned that I'm not a good businessman, but it was a good learning experience in terms of how OSU may proceed with that. On the side of the research, I'm really excited. We are working on some experiments where we will have 10 feet by 10 feet concrete slabs in the lab, and then we will probably have 6 or 8 inches, and we will put these hollow bars, solid bars, and then we will circulate the air, and we will have the evidence in the lab. So as we were doing this research, we found out that there are a lot of products out there already to heat concrete, whether it's a slab or pavement or wall, as you can see on the picture. There are those commercial products, but all of them have plastic cables or some kind of heating cable inside the concrete. And in our case, for example, if you look at that wall or even the slab, in our case, we are trying to eliminate this double effort. We already have the steel in there to carry the loads, right? So why not include the heating aspect to that? So the advantage is we will eliminate this entire heating business if it works. So that's what we are working on. So I'm really excited about this project. We are at the beginning stage right now. So oh, by the way, this is a little bit unusual. I will just keep changing gears. Normally, I give a presentation on a specific topic. Today, I have at least 8 or 7, maybe more different topics. I will just jump around. Sorry about that, because I'm just trying to show what I have done over the years or what I'm doing right now. I have a PhD student. Right now, he's very interested in fiber reinforced or FRP bars. Um, and some of you guys may be aware, but ACI has a code on use of FRP bars, and they came to state of Ohio. They wanted to get approval through before IBC for use of these bars for category one or non-critical concrete structures. Ohio did not approve it, and they delayed it for a couple more years because it's just coming into the picture. But within the next few years, these are going to be more and more common. It is coming right now. In some states, they already adopted, or like places like Florida or South Carolina, they face it, a lot of corrosion problems, and this is becoming more and more common there. So the good thing about these materials is they are corrosion resistant, so we don't need to worry about those type of durability problems. And then they can be lightweight as well. But since it is a new material, there are a lot of problems out there. So right now, my PhD student is thinking about lap splices or mechanical couplers and some other issues, bond issues between concrete and these bars. One disadvantage of these materials is that these are brittle as opposed to standard steel bars. But again, this is coming within the next 20 years. You will see some of these bars in bridges and buildings. So we like to be part of the research as we see the applications. One of my graduate students a few years ago worked on a project where we wanted to use this regular steel bar, but we wanted to provide some protection against corrosion in the field. So the idea was to take the steel bar and put these fiber reinforced polymer sheets on the bar. So if you follow the red arrows, we can see the process. So we used epoxy and we glued those FRP sheets or layers on the bars. And then on the lower left corner, you can see those glass fiber bars and then the carbon fiber ones. And then we did quite a bit of corrosion test. Intentionally, we introduced those notches on regular carbon steel and also green epoxy coated bars. As you can see, those notches are done intentionally. And we put them in acidic solutions. Actually, some of them are still in our lab. I think this is already 5, 6 years. And student is, although he graduated, he's an engineer in town. He comes every year or something like that, and he sees, he checks the corrosion progression in the bars. So we also created notches in our FRP wrapped bars just to see how the corrosion is progressing, whether we are successful in stopping the corrosion. Interestingly, I didn't put the pictures, but even the epoxy bars really get corroded. That's what we are monitoring. The green bars that you see here, right now, when we go to the lab, that the little portion has a lot of corrosions spreading under the epoxy over the years. So these are the strength tests that we did. If you look at the end of the elastic portion, that purple color S1 is the regular bar. That's the only advantage that we get. So that bar not failed, but yielded at around 24 kips. That you can barely see that purple colored line, but the other ones reached all the way up to 30. So as long as we can keep our steel bars in the elastic range, or if we hit the limit, they did a good job. But since we did not do this professionally, unfortunately, after we reached the peak, we lost the contact between rebar and FRP, and then the remaining portion acted like a regular bar. So if we wanted to move it, manufacturing these type of bars, then we learned that we needed a better bond between the FRP and steel bar. But at least we proved the point that we can increase the strength up to the yield point that was the case. And the graduate student ended up doing some beam tests, as you can see down here. The bond between the concrete and these FRP wrapped bars were excellent. So that was very good news. That was even better than the regular bars. So it was promising, but again, somebody has to do this professionally. We did this technically and we were done. So I just wanted to pull out there as part of our research. Here's another project that we did a while ago. The idea was everybody is aware of the standard reinforced concrete reinforcing cage, right? On the left-hand side, we have the longitudinal bars, we have the transfer steel, let's say in a column. Our idea was, can we replicate that using solid steel tubes or solid material just to speed up the construction? So that's how the idea started. And the good news about these steel tubes is we have a lot of flexibility. All of these tubes that you see on the screen represent some kind of reinforced concrete or reinforcing cage, whether you have 8 bars or 12 bars, and then depending on the spacing of the transfer steel, the amount of steel, we can put less steel, more steel. We can play with the thickness of the tube. So we played around with all of these. As far as production is concerned, it was relatively easy after we found the location. This is laser cutting. Apparently, there are other options, water jet and things like that. So the good news is the labor is completely automated. So you just define the size of those holes on the computer, and this machine just goes back and forth and just cuts those pieces for you, and then you got the reinforcement ready. So then we did quite a bit of tests on those columns, and then we moved to repair and retrofit of existing columns. We thought that may be a little bit advantageous scenario. So we took a standard circular column or its scaled version on the left-hand side, left end. And then we added either concrete jacket or another concrete layer with regular reinforcing concrete, regular reinforcing steel, as you see at the top. And then we used our own new idea just to see how these two reinforcing systems would work. So we thought this may be a little bit easier to implement in the field. So again, on the left-hand side, you can see the column specimens before we retrofitted them. And we also used regular FRP laminates. And this is almost like common these days for retrofit purposes. Even on campus, if you are familiar with it, Total Garage has some of these laminates to strengthen the beam column joints if there are students joining today. So if you go to that Total Garage across from Stadium and Knowlton Hall, if you look at the joint regions, they painted in the concrete color. It's not so visible, but on the second floor, third floor, you will clearly see that there are FRP laminates there just to increase their strength. So we use them in our retrofit purposes. We also use, this is another project with another student. I'm jumping around, I realized. We use those laminates intentionally. I put this beam column joint in the middle just to show that we also did some work on other components using these fiber reinforced polymers. So on the top left corner, you see the original beam column joint. In our labs, we pushed the pulled and pushed that cantilever portion. And then in the middle figure at the top, you see the damaged beam column joint region. And then on the right-hand side, you can see how we fixed the cracking. So this can be a scenario, let's say for seismic or some other extreme loading, your beam column joint may be damaged the way that you see in the middle photograph. And then on the on the right-hand side, we cleaned up the concrete and then put the new concrete in there. But obviously that concrete and the joint region is much weaker. Then we applied the FRP layers, as you see in the lower portion of the slide. So we had those little bit of diagonal FRP layers, and then mainly in the beam portion. We also had some kind of anchorage at the ends of the FRP layers. You can also see those tapcons on the picture. So this was also another good study that just to show the effectiveness of FRP on for retrofit purposes. So going back to our column specimens, in addition to our regular concrete jacketing, including both traditional rebar cage as well as our steel tube idea, we also had a few specimens retrofitted using this glass fiber and carbon fiber, as you can see on the screen. So there are two possibilities for this. One is wet layup, the other one is already ready-made. We have some companies, let's say Simpson Strong Tie in town has they donated the material. I am acknowledging them in an indirect way as well. So they are quite big in the business, and they do quite a bit of work actually in Central Ohio out of their office in Columbus. So what we did was, or the graduate student did was, he used the epoxy that you can see that yellow colored material inside the bucket, and then put that fabric material and then put it on the column and then waited about, I believe, 30, 40 minutes, and then it hardens, and then it works quite well under axial loads. And then we also tried steel tube. This is commonly done in the bridge piers. So if there's a damage or if they want to increase the strength of the piers and bridges, they typically bring these steel tubes, especially in California or West Coast for seismic purposes. They add this and then they put some kind of a grout between the steel tube and the original column. That's what we did. And these are the two that we used inside the concrete jacketing. The top one is our new idea that no one has used. And then we were trying to compare that with the standard concrete jacketing with the traditional rebar. So to our surprise or not surprise, the results were quite comparable and our idea did quite well. I think I have some results on the next page. So I'd like to move on, but let me comment on this little bit. That green line at the very top is the best one because steel tube provides perfect confinement. So it does a very good job. And then the pink and the red one is our idea, that tube with the holes in them. And the blue one is the reinforced concrete jacket. So ideally, we were trying to see how pink and red lines, which is our idea, will compare with the reinforced concrete or the blue one. Overall, they are quite comparable. Actually, we had many more experiments. I'm just showing you one case here. So we were a little bit on the lower end with the strength, but stiffness was a little bit larger. And then in the post-peak range, our system did much better because of the confinement that it provides to the system. And then those black lines, the dotted and dashed lines are the FRP ones. So let's not compare them directly because it becomes apples and oranges, because those colorful plots are providing additional concrete and steel versus FRP layers are on the member, but they are still very effective because the original column or specimen is the solid line. If you look at the FRP, it increases the strength quite a bit. As I mentioned earlier, FRP does a good job whether it's a bar or the layer, but at the end, it's a brittle material. As you can see, once you reach the peak, it fails suddenly. So if you end up using those FRP materials, whether it is retrofit or bars, you need to be very careful with the brittle failure mode. So that's what the ACI is trying to address in the design code that is coming up. So maybe I can spend a little bit less time here. So these pictures are showing right next to each other equivalent conventional rebar cage versus what we proposed. One advantage of our idea is faster and easier. Obviously, that saves some money for labor. And then in terms of structural performance, they did quite well and as comparable. In some cases, it was even better than the standard steel bars. Well, suddenly I'm changing the gear. I'm sorry. This is very unusual. Normally, I wouldn't just jump around like this ones. As I said, I got my PhD in California. There, everything is seismic. So every single structural engineer has to consider seismic as the first step, right? I started moving away from seismic as I moved after I moved to Ohio, but still, it is still part of me. And whenever I get an opportunity or whenever my students are interested in earthquakes or seismic, I always go back there. So there was a major earthquake in Turkey last year in February. This was a very big event, a very unusual event. Turkey is a very highly seismic region, but even this one was something that they didn't see for the last 80 years, 80 plus years. So fault rupture was almost 250 miles. That's very, very unusual. And the return period for this region was 200 to 250 years, depending on the location. So that means those people or that those regions did not see such large earthquakes for maybe 150 years to 250 years. So this is similar to 1906 San Francisco earthquake that even California or US did not see such an earthquake for more than 110 years. So just to highlight that. During the earthquake, almost 19,000 buildings collapsed immediately. And then I think they demolished another 30,000 buildings shortly after the earthquake. They were severely damaged. And then that area was affecting more than 14 million people. And then 56,000 people died. That's a huge number as well, just to show you the effect of the earthquake. And Antioch, that I never been to that part of the country, but is apparently a very old city, older than many other cities in the Middle East. So I was surprised to learn some of the history. And that city is, I will say, 70% destroyed, just to show one picture on the screen. So this was the heart of the damaged region. So we spent Earthquake Engineering Research Institute funded our travel. 18 structural engineers went there, and 6 people concentrated on hospitals. Maybe I can quickly tell. Oh, I assume many people are structural engineers here, although we have civil engineers, I know. Base isolation is a new technology being used in Japan and other places, but US is a very conservative place in terms of structural engineering. Unless there's a very critical historical building or something very unusual, if that's the only option, people use it, but we try not to use these new technologies, and we try to see how it is going to work in other places before we invest a lot of money. So Turkey required all new hospitals to have base isolation in 2012. So it was a big real test for Japan or all these high seismic regions, and they sent all their people. So since it was such a big thing, 6 of the 18 engineers were specifically focusing on hospitals. Some of the older hospitals collapsed and all kinds of damage, but surprisingly, or maybe not surprisingly, those base isolated structures did very well they were fully functional even in a highly hit region. So that's quite a bit of learning experience for everybody around the world. So the other six people focused on lifelines, bridges, and power lines and dams and things like that. And I was leading a group of six people on building performance, and we spent 6 days in the area. As you can see, those red locations are bigger cities, and we ended up spending a lot of time at more than 150 structures where we want to learn more. We did a lot of documentation. And at the end of May, in let's see, in couple months, we will go back there again. ERI wants to, or we like to learn about functional recovery. So what happens after 1 year? So it is also documentation of resilience of those cities. So your building may be perfectly fine, but if schools are closed or if there's no grocery store, those kind of issues, as civil engineers, we can do a good job, but because of other effects, are they really functioning? More specifically on our end, we will be checking these 120 structures to see if they are back to normal or they are retrofitted or they are demolished. So we documented before. Now after 15 months or so, we will go back again and then see what happened to those buildings. So the big question for us or for our group was, why did these 18,000 buildings collapse? And why did another, I don't know, X many buildings are severely damaged? So personally, I'm a little bit biased because my research focuses mostly on columns. And I can tell you that hundreds and maybe thousands of people died because of failure of those columns. So my focus is a little bit on the columns, but other structural engineers were focusing on shear walls and the system behavior. So we divided different issues among ourselves. So again, on my end, I could see tons of issues with the detailing of the columns. Another major learning experience for me was that the details of these columns are very similar to what we do in Ohio. So they are designed, especially before 2000, they were designed to carry mainly gravity loads. Although it was a seismic region, especially for locations away from the fault line, they didn't pay too much attention until 2000. After 2000, code change and they improved the process, but still there were a lot of buildings. So at the end of the day, this was $1 million learning experience for us to see what happens to our structures if something like that happens in a low to moderate seismic region. So again, we use 90-degree hooks if you are designing concrete structures, and that's perfectly fine for us. And we put our column ties at 18, 20 inches in Ohio. Oh, by the way, when I moved to Columbus in 2002, after I lived like 6 years in California, I thought all these buildings will collapse. So I took the students to Scott Lab and some other campus locations for a visit as part of my class. I'm like, oh my God, they use these 90-degree hooks, column ties at every 18, 20 inches. It was unimaginable, or it is unimaginable for an engineer in Los Angeles or Seattle or San Francisco. Well, these are perfectly fine for our region because earthquake or some other risk is very low. But if it happens, now you could see what happened. All these buildings develop plastic hinges. I just copied a couple examples. Oh, another one is the splices. You see here, what we do is either above the foundation or above the floor slab, we cut our bars coming from the bottom floor or foundation about 3 feet above the slab level. And that's perfectly fine since we don't have major risk in Ohio either because of wind or earthquake loading. And if we are mainly focusing on gravity loads, that's fine. But if you subject your building to a major lateral load, as you can see here, this building was almost on the verge of collapse. So those lap splices create a major weakness. So if you look at the picture on the right-hand side, just because of this, I can say hundreds of buildings collapsed. So again, this is a typical gravity load design versus if you subject your structure to lateral forces, this is not so good. Again, this is obviously not allowed in California or high seismic regions in the US. That those lap splices should be within the middle portion of the column. So the reason I mention this is whether 90-degree hooks, lap splices. I know some people, I recognize a couple names. If you are designing government buildings or critical structures, even in Ohio, I strongly suggest change the design a little bit, go to chapter 18 of ACI and improve the properties. So you never know if something goes wrong, we know what to do, but we are not required to do in Ohio because luckily, actually, Ohio is one of the lowest risk regions in the US in terms of all kinds of wind loads, seismic loads. We are very lucky. Snow, wind, seismic, when you look at all those hazards, flooding. So we are very, very lucky if you look at the combined hazard map in the US. Okay, so as I said, my background and my research has been on columns, reinforced concrete columns. We have three possibilities for column response if we push it in the lateral direction. We like to design all of our structures the way that we see on the left-hand side. We like to see that plastic hinge and damage concentrated at the bottom. And then we like to confine those regions with a lot of transfer steel. So that's another reminder if you are in design business, please, I tell my students when they take my classes, try to use circular columns if architects or the owners allow you, and that spiral provides a lot of confinement, and your lateral load displacement data is going to look like the one in the bottom left corner, where if you just keep pulling and pushing, your steel is going to yield. Since you have a lot of transfer steel, it is going to confine your concrete. You will have a nice ductile behavior. Versus if you go to the other end, to the right side of the picture, then you have those diagonal shear cracks, especially in short columns, or if you don't have enough shear resistance, then it will be brittle failure. It will be elastic, and as soon as you reach the capacity, boom, it will fail. So we don't want that. But in Ohio, again, if there are lateral forces, there are possibilities for those. Luckily, we have low risk, as I was just mentioning. But even in structures, in many structures in California, if they were constructed before mid-1970s, they did a very good job and fixed schools, hospitals, government buildings. But there are quite a bit of privately owned reinforced concrete structures with details similar to in, let's say, in Ohio or the middle column. So that was my research. That's how I started, where the column that you see in the middle is representing almost exactly what we do in Ohio. The spacing of the ties were 12 inches, 90-degree hooks. Oh, by the way, the person in the picture is my advisor. He just retired last year. And so those columns, or the columns that we have in low seismic regions, or actually around the world, there are so many, even in high seismic regions, if you look around like Indonesia to India to Mexico to Chile, everywhere, when you see some of those buildings collapsing, when you look at Google, you recognize, oh, I just saw from last night, there was a major one in Taiwan. I didn't see column pictures, but very likely they had poor details like the middle one. Poor seismic details, I should say. So with those columns, we can reach the flexural capacity, but when it comes to shear under very large lateral forces, we lose the shear resistance very quickly, and then we try to figure out what happens under axial load. And the next question is, why do we still care about those columns under lateral loads? As I said, there are so many of them all around the world. And also, if something goes wrong, let's say in low seismic regions, I just keep saying Ohio, let's say Ohio, then we also need to understand what is going on. One of the major reasons that I had to do research was if somebody wants to upgrade a structure in West Coast, a high seismic region, they need to understand the existing capacity. To do that, they need to consider those shear effects because that has a major contribution. I had at least 3 or 4 graduate students, focusing on this research over the years. If you look at the top right corner, we developed computer models for bar slip at the end of the column, where you see the bar slip and the shear behavior, and we try to predict and estimate the existing strength. And if you design properly, detailed columns, then our computer programs can take care of all the models that you see down here. So these are the models that my students developed over the years. And this is probably the end of my seismic discussion. And the report on the report on the left-hand side came out a few months ago from the after summer regarding that Turkey earthquake last year. Oh, we have another faculty member, on the geotechnical side, Patrick Bassal, and he is involved in at least 2, 3 chapters in this report. If you are interested, all the details, starting from ground motion to soil to structures, they are all included in that report. So again, after I moved out of California, my interest in seismic is slowly going down. But then I found another area, which is the progressive collapse. So I realized it's very easy to move from seismic to progressive collapse because of construction issues or some other issues, impact, blast, fire. We end up losing a column or two, and then suddenly we see partial or progressive collapse. See, for seismic design or seismic assessment, we already deal with this issue. This was my research area. If you lose a column or two, what happens to your structure in a seismic situation? So we already know that sometimes our buildings collapse, sometimes they don't. So I started doing research at OSU, and I established a relationship with the university engineers and architects, and we ended up testing 10 actual buildings. I believe 7 or 8 of them were on campus. So this was one example that the university demolished a while ago, and I worked with them, and the demolition company cleaned up the walls around those columns on the first floor level. And then we instrumented the building, and then we asked them to remove that column. And you can see in the bottom right corner that the column is gone. During that process, we could see what was going on, or we could see how the load on that column was redistributed within the building. So, and then we have all these computer simulations. Again, I think I had at least 4 or 5 students doing research on similar things. This one shows the floor plan for this building. That red cross is the column that we removed, and all the other numbers are showing the locations of our displacement sensors and the strain gauges. And then again, that red cross is showing the removed column. So we know exactly how much load was transferred to the other columns. So I can tell you roughly that if we had, let's say, 100 kips on that column, roughly 30 to 40 kips goes to the 2 neighboring columns, and the remaining 30 or 25 kips goes to the interior. So this is a typical computer model out of SEP 2000, and you can see what happens to that specific region or the beam above that removed column before and after. So those colorful plots are the measurements from our strain gauges, and then we have the measurements. Ooh, it looks like I'm running out of time. I'm sorry, I spent a little bit too much time. So we had another experiment where we removed 3 columns one by one, and then these are the dorm buildings that the university demolished about 5-10 years ago. Oh, some of them are still standing. They demolished a few, and we did experiments on masonry buildings. And if you look at, I also collaborated with our geodetic science folks because these buildings did not have any columns. So we monitored the deformation of the walls using all those little white stuff put on the walls. Those geodetic people in our department help us monitor the response, and these are the models that my students generated. I also like to show a few projects very fast. I have one student defending his PhD dissertation tomorrow. This is not his research, but he extended this research on seismic response of nuclear structures. There's quite a bit of effort and funding after Fukushima, and then they have a lot of concrete components and structures in there. So we looked then to different scenarios in this nuclear facility. For example, what happens? We looked at the 3 realistic scenarios that nuclear engineers told us. So if you have equipments at different levels of the concrete structure, if you look at case study 1, they were very interested in the functionality of those equipment, and our students can easily calculate the demands and capacities. And then another case study was the crane at the top of that container structure, case study 2. And then the third one is apparently they have some water tanks next to the building. What happens if those tanks fail and then flood the basement of the structure? Over the years, I worked with ODOT, but then I started working with Federal Highway Administration. Again, I never thought I would get into culvert research, but we ended up testing, let me see, almost 50 culverts in the field. As you see on the picture on the right-hand side, we brought these heavily loaded trucks on the bridge or on the culverts. We tested a lot of metal culverts, concrete pipes, plastic pipes, and then we instrumented them like the way that you see on the picture, and then we could measure all the strains and displacements. And then after we get the field data, we could develop these three-dimensional models. I've worked with geotechnical engineers or geotechnical engineering professors with soil structure interaction because they help with the soil models, and we worked on the structural aspects. And we got a lot of useful information on joint design for AASHTO, and then also ODOT got a lot of useful information about load rating of these structures. And then these are computer models for different joints and other components of the culverts. I was also involved, again, I wasn't intending to do that, quite a bit of pavement research. And I found I enjoyed it because I found out that the properties of these asphalt concrete is not too different from our regular concrete. So ODOT had a lot of cracking and unusual failures south of Cleveland in that region. And then there were some smaller projects, and luckily, there were pavement engineers involved in this, and I was involved in testing of some of these things. And it was a great learning experience about how the pavement materials and the strength works. And I learned quite a bit about pavements as well. I had a couple of students looking into sustainability is a big deal for us, looking into different plastic materials and whether we can use them in concrete. This is a real problem, by the way. We did this lawn chairs, plastic utensils, keyboards, and some other plastic materials that I will show you on the next slide. But see, one company approached us. They are recycling all of these computer boards out of our PCs and medical equipment, and they are located 1 hour or 90 minutes north of Columbus. They have tons of these green computer boards. What they do is they take those computer boards and they take all these metals out of them. Apparently, they have all kinds of valuable copper-like materials. And then they don't know what to do with these carbon fiber type materials. And well, maybe just to let you know right now, I do have an industry funded project right now that also came out of a need. This is a local, not local, but somewhere in the state production facility. They waste so much material every single day, plastic material. It all goes to the landfill. They approached us and they said, can we use this in a useful way? So they are paying us right now. Hopefully they will go to mass usage. They will buy the equipment. And right now we are doing the validation in our labs. Oops, I'm sorry. I'm almost done. This is, I have a couple more slides. So the students tried all kinds of plastic materials to see how they were affecting the strength and stiffness of the concrete materials. We did tons of little cube specimens by replacing the cement. And then we did the cylinder specimens using the sand-like material, and we did the beam specimens. I'm mostly on the structural side. I collaborated with one faculty, actually three different faculty members. I'm collaborating with somebody in industrial engineering with polymer and plastics expertise, and Lisa Burris in our department is the expert in concrete materials and chemistry, and I work with her quite a bit on some of these projects. So this is also exciting that there's a real need out there to solve the problem. So this is the end of my presentation. I'm sorry, I was supposed to finish a little early, but it looks like we have 8 minutes for questions if you want to finish at 1 p.m.
Thank you very much, Halil. So I'll invite folks on the call. I think we're a small enough group. If you use the raise hand function to join the conversation with questions, or you're welcome to put things in the chat. There is a question from earlier in your presentation, Halil, which is to ask how the circular steel cage jackets would be installed on existing columns.
Okay, the good news is it is already being implemented in the field. So what they do in California is they have these two C-shaped pieces, and there's an existing circular column, right? They typically bring those two C-shaped steel, I don't want to call it tube, but steel channels, something like that, and they bring them together and they weld all the way over the height of the column. So that's the standard practice that they do in California. They have quite a bit of steel jacketed column or bridge piers. So that's the easiest answer. There may be some other ways, but that's what they do in California. I apologize. I had to rush a little bit near the end. So, but at least you got the flavor of what we have been doing in our labs.
Any other questions? Well, thank you, Halil, for closing out this year's series of seminars. And those on the call, I invite you to look for the announcements in next academic year when we'll pick up our quarterly schedule again with the first seminar likely in the mid-September range. So we'll get that information out to you late in the summer, and hope to see you at one of those presentations. And just a reminder that those of you who requested CPD hours as part of this session, those certificates will be out to you in about 2 weeks. Thank you to everyone who could join us today.